Today we have an interesting topic on physical science and mainly physics. So in this particular topic we'll be looking at current electricity. Now before we define current electricity, you will notice that electricity is quite a loaded word. What do I mean by that? I mean there are different kinds or types of electricity. Now if you recall, there's a topic called electrostatic induction, which is basically static electricity. So this is a continuation from that particular topic. So it's important that you know how to make the distinction between the two because they are not the same. So having the background understanding of static electricity, it will help you to build up your understanding when it comes to current electricity. So maybe taking us back to what static electricity is. So in that particular topic, we were looking at insulators or what you call electrostatic induction. So this is basically, or in simple terms, electrostatic induction has to do with the process of experiencing the transfer of electrons through insulators. Yet, what we're going to be looking at today in current electricity, it is mainly now looking at the transfer of electrons or the movement of electrons in conductors. So it's important to understand the difference between an insulator and a conductor. So these particular illustrations on the board are trying to explain the difference between an insulator and a conductor, because this will be an important point in the basis of our explanation. So in static electricity, we noted that this was the electricity through insulators, and in the sense that insulators are made in such a way that the charges are in fixed positions. So mainly when we are talking about current or when we are talking about the transfer of charge, we'll be basing our transfer of charge on electrons, not on the positive charges. So if you look at the charges in this particular illustration of an insulator, the negative charges are fixed in one position and the positive charges are also fixed in another position. And you'll recall that in static electricity, you need to rub that particular object with another, and then there will be the transfer of the negative charge. And that negative charge will be transferred into the other, and still, after that transfer, it will be fixed in that particular position. Now, in comparison, if you look at conductors, in this case, you need to recall your chemistry, metallic bonding, where we note that metals are made out of positively charged ions and in a sea of delocalized electrons. So what do we mean by sea of delocalized electrons? We mean there are many electrons which are free to move to and fro within that metal. So in conductors, the electrons are not fixed, but they are able to move from one position to another. So that's the difference between static electricity and current electricity. In current electricity, the electrons or the negative charges are free to move. They are mobile, so they can carry the charge. And which is why the next part in which now diving into current electricity, we want to define what is current. So the definition of current is the flow or the rate of flow of charge. So the key words is rate of flow and then charge. So the rate of flow of charge. Another definition that you can use, you can also say it is the flow of charge per unit time. So which is why the formula or the equation for current will be I is equals to capital letter Q over small letter t, where I stands for electric current and capital letter Q stands for charge, and the small letter t stands for time. So please note that this formula is very important that you write it exactly as it is, because in physics we are very much particular when it comes to the symbols of equations or symbols that represent different quantities. So the capital letter I stands for the current, and then the capital letter Q stands for the charge, which is in coulombs, and then the the small letter t stands for time. Remember, in a capital letter T represents the period, so you shouldn't confuse it with the small letter t. Now, what are the units for current? And also we want to look at what instrument do we use for measuring current. So the units for current are called the amps, even though some, maybe it can help you to write the spelling. Some will pronounce it as amperes, but pronounce it as amps. The R-E-S is silent. So amps, and it's a capital letter A. You'll notice that, in fact, A is equivalent to C, capital letter C over S. Now C over S stands for coulomb per second. So in other words, the reason amps are equivalent to coulombs per second, it is because the units for charge are C, capital letter C, and the units for time, it is S. So therefore, this gives us the units for amps to be also equivalent to coulomb per second. So this is basically important, especially if you want to change the subject of the formula, especially when you are required to calculate charge. Because when you make charge the subject of the formula, you multiply by IT so that you get your answer as a column for charge. Maybe I will give an example for that. So we're saying current is the rate of flow of charge, and this is the formula. So here's an example. Let's say, for starters, you are given that the charge, or maybe let me demonstrate how you can calculate the charge. So given that the current is, let's say, 2 amps. The current is 2 amps, and you are told that the time is 1 minute. Calculate the charge. So what would be the charge? So let's say this is a current flowing within a circuit in 1 minute, and it is 2 amps, the current that's flowing within that particular circuit. So you are asked to calculate the charge. So what do? You write current is equals to charge over time, and then make charge the subject, so which means you'll multiply both sides by T. So therefore the charge will be equivalent to IT. Now before you attempt to answer, it's important to note that the time that is given is in what? It's in minutes. So yet our time should always be in seconds. So you need to convert this minute into seconds. So you know that 1 minute is equivalent to how many seconds? 60 seconds. So therefore, we will multiply the 2 amps by 60 seconds. So this will give us an answer. So I want to show that the answer will be the capital letter C. Remember that the current is amps, which is equivalent, it's 2 amps, in which case amps is equivalent to C over S. So this is the same as saying 2 C over S multiplied by 60 seconds. So mathematically, this S cancels that S. So 2 times 60 is 120, and here is the C. So that's why we are getting the answer for charge as 120 coulombs. Now you might be wondering, where is the coulomb coming from? Coulombs is basically based on the person who discovered this. He's a French physicist and mathematician, Charles Augustin de Coulomb, who came up with these units. So now I want us to continue and look at other quantities that are related to current electricity. So that was the units. So what is the instrument there for measuring current? You will notice that the instrument for measuring current is called an ammeter. An ammeter is the instrument that you use to measure current. And I will demonstrate how it is connected through what we call the basic circuit symbols, and the difference between the types of circuits that we have. So for starters, we're just looking at the main quantities under current electricity. So that was current. Now, the next quantity is called voltage. Now this one is interesting because it is divided into two sections. You have what you call EMF, which stands for electromotive force. And also in voltage, we have what you call potential difference, or what is called PD. Potential difference. PD stands for potential difference. So what is voltage? In simple terms, voltage is the source of current. So in other words, you cannot have current without voltage. Now, it is divided into two because the electromotive force, it is the voltage that is still in the source in chemical energy state. What do I mean by that? If you are looking at a cell or a battery, there's a difference actually between a battery and a cell. When you're talking about a cell, it's just one source, like for a 1.5 volt cell. But once among two or more, you now call that a battery. In other words, a battery is the plural for cells. So, or rather for a cell. So, abamaneng we call it battery, but wabayinye is just a cell, although we normally use it interchangeably. So, an electromotive force, this is the total electrical energy supply. Total electrical energy supply. Energy supply from a specific source. So there are different sources of voltage. The cell is an example of a source of voltage. A battery is an example of a source of voltage. And also there is a topic on magnetic induction where we have generators. A generator is also an example of a source. So basically in this state, that means it is a state where it is still in the chemical state, chemical energy. So in a battery, the voltage is the source, which means it hasn't changed into electrical energy yet. It's still in chemical energy. So that's why we're saying EMF, it is the total electrical energy supply from that particular source. And then the potential difference. Now this is the driving force or the work done in electrical energy. So this is the work done in electrical energy. So, and this involves also what you call voltage drop. So this is the work done in electrical energy. In simple terms, this is the voltage in which it drives the electrical energy, or it drives the charges of each column across that particular circuit within a conductor. In other words, the potential difference, it is the current flowing, or it's the voltage that is within the circuit. Then the EMF, or electromotive force, it is the electrical energy stored in a cell. That is why we call it the total electrical energy supply. But once you move saying current, meaning it's flowing now within the circuit, it becomes the potential difference. Which is why the reason it's also called potential difference, it is because it is the electrical difference between the two potentials. The electrical difference. You'll notice when I draw the circuit, you will have a positive terminal, so it's the electrical difference between the potentials of the terminals. Electrical difference between the positive and the negative terminal. Again, you will see this. You'll see this when I draw the basic circuit. So a question can ask you, what is the difference between, what are the similarities and the differences between electromotive force and potential difference? You should be able to explain that the electromotive force is the total electrical energy supply, and it is in chemical state where it is stored energy either in a cell or in a battery. And then the PD, or the potential difference, this is the work done in electrical energy. Or this involves voltage drop, which is the flow of the current or the voltage within the conductor. And also you can say it is the electrical difference between the two terminals, which is the positive and negative terminal. The similarities is that both of them are measured using a voltmeter for the instrument. Both are measured using a voltmeter, which is the instrument, and the units are volts, which is normally AV. So this is voltage. Now, the last electrical quantity that we'll be looking at is resistance. Unless, of course, there's a question, please feel free to ask. So resistance. What is resistance? So as the name implies, my resistor is opposing. When I talk about any resistance, there is an opposition or an altercation. So in this case, because we're looking at electrical phenomena or quantities, or rather current, electricity, a resistance would be an opposition to current. Opposition to current. So this is what opposes the flow of current. Why is there an opposition to current? If you remember, in Form 4 physics, the reason why you learn about the forces way back before you reach this particular topic is because once there is a movement, there is a force, and once there is a force, there is another force that will oppose any driving force. And usually it becomes, the opposing force is the force of friction. So in this case, you can also explain the resistance in terms of as an opposition or a frictional force. Because what it does, it opposes, in this case, the flow of current. So there is always an inverse relationship between resistance and current. This is one of the reasons why there are different materials that are used in making certain conductors, so that we are able to reduce this value in terms of the efficiency of the current flowing within that particular conductor. Now, a resistance here, let's start by stating how do we measure it, also the instruments. Now there are two types of resistors. Mainly the instrument is the resistor with an O. There are two types of resistors. You've got a fixed resistor, and then you also have a variable resistor. Now a variable resistor is also called a rheostat. So that's another term for a variable resistor. Now a variable resistor is also called a potential divider. So which is where you will see why if voltmeter can also be connected, can only be connected across a cell or a resistor. It's because it becomes a potential difference divider. So anyway, you'll see this when I draw the basic circuits. Right. Then also under resistance, there is what we call resistivity. Remember, I did highlight that there is a reason why different conductors or different materials are used to affect the value of resistance. Or I can simply say materials can affect the kind of resistance that will oppose the current flowing within that material or conductor. So resistivity becomes that value which depends in that particular material. Which the resistance of the material is dabangana. So resistivity is a constant, and it is given by this symbol which is called the rho. It looks like a slanted P, rho, and it is affected by two other quantities. And these quantities are length and the area, surface area or cross-sectional area. So they are affected by length and cross-sectional area. Cross-sectional area of that material. Cross-sectional area of that material. So I've run out of space here. Let me raise the top so that we can continue. So, how does length and the cross-sectional area affect the resistance of a material? So, for length, there is a direct proportional, or there is a direct relationship rather between resistance and the length, and there's an inverse relationship between the cross-sectional area and resistance. So mathematically you can represent this like that. So R, and write alpha to L for length, then cross-sectional area, there is an inverse relationship. Let me first write it in simple terms. The longer the wire, the more resistance. The shorter the wire, the less resistance. Then, because there's an inverse relationship between the cross-sectional area and the resistance, the thicker the wire, the less resistance. Thicker, less resistance. The thinner the wire, the more resistance. So thinner, more resistance. Longer, more resistance. Shorter, less resistance. Thicker, less resistance. Thinner, more resistance. Now let me explain why is this the case. So remember, I was saying the resistivity is the ability of that particular material in opposing resistance, or it's that specific, it's a specific value depending on the material, on how it will affect the current flowing in that particular conductor or material in terms of resistance. So I was saying the length will always have a direct proportion. So how to explain this? So when a wire is longer, remember also this is a conductor. So if you have a longer conductor, there will be more current that will be flowing in. So because there will be more current that will be flowing in, that would mean there will be a greater collision of the charges. Remember, the flow of current we see is the flow of charge, or rather current is the flow of charge. So this collision will cause a lot of resistance. So, and that particular resistance will also register normally as heat in that particular conductor. So hence, the longer the wire, the more resistance. But when the wire is shorter, then there will be less charge that is flowing in there, and therefore there will be also less resistance. So that's how we can explain why do we have a direct proportionality between resistance and the length. Now coming to the cross-sectional area, how to explain this? Maybe let me also draw some illustrations here to make it easy. So the difference between a longer, so let's say in this case, because the variable that I am focusing on is the length, so that means they will have to have the same diameter or the same cross-sectional area. So this one is shorter, this one is longer, and they both have the same thickness. So you notice, like I was saying, if it is longer, there are a lot of collisions here, causing a lot of resistance. But here they are shorter, there are a few charges, and therefore there is less resistance. Now in this case, the thicker the wire, the less resistance, and the thinner the wire, the more resistance. So in this case again, how do we explain it? Thinner, mala, thicker. It's easy to explain this. Let's say you are invited to a party. And in this party, we will say two cases, two parties. One party, like they are all filled up to capacity. But in the second party, there are only a few There are only a few people there. So this means, or maybe let me ask you, ule party lapho kuna bagcwele baminyetela, will it be easy to dance or move around? It won't. So lapho it's a case where it is thinner because and that's minyetela, it's not easy to move. So because it's not easy to move, we are causing a lot of collisions and resistance. So that's why the thinner the wire, there will be more resistance. But in the second case, where that party, there are only a few people who are there, you can do any dance move anyhow, and there is a lot of room. So in that case, that means there will be less resistance. In a thicker wire, there are less collisions, the charges are free to move, and therefore there is less heat that is created there, or less resistance to that flow of charge. But when you have a thicker wire, or rather a thinner wire, then there is more collisions there, which is causing the resistance, and therefore the thinner the wire, the more resistance, and the thicker the wire, the less resistance. Now, to summarize this is summarized in this following equation. Now, your syllabus only requires you to understand the difference or how length and cross-sectional area relates to resistance. Otherwise, in some syllabuses, you find that you can also do some calculations. Okay, so this summary of an equation is like this: L over A. So remember, this is the resistivity, which is standing for, which is specific to each specific material on how it is made. And then R stands for the resistance. Notice L is in the numerator, meaning there is a direct proportionality between resistance and length. And then A is in the denominator, which simply means resistance and the cross-sectional area. They are inversely related. Fine. Now, basic circuits. Basic circuits, symbols, circuits. So basic circuit. So in this case, let me just start by drawing a simple circuit so that you will see the different kinds of circuit symbols that we shall use, so that we have. So this is a positive terminal. And then we shall have the amps, and then we can have here a variable resistor, and then we have a fixed. So let's say this is a simple circuit, a simple closed circuit. So this is where, remember I said you can only connect a voltmeter across You can only connect a voltmeter across a resistor or EMF or cell. So in this case, this is a battery because in fact we've got two cells now. The first thing also to note is that this is conventional flow. Maybe I should also explain this. There's a difference between electron flow and conventional flow. So conventional flow, when we're talking about current electricity, we simply mean that the current kusuka from the positive terminal to the negative terminal. So this is what we call conventional current flow. But electron flow, this one is illustrated in chemistry in a topic called electrolysis. So that is where the flow, it is mainly electron flow, which is from the negative terminal to the positive terminal. So that's the difference between electron flow and conventional flow. Conventional flow is current flow from positive terminal to the negative terminal, and electron flow from the negative terminal to the positive terminal. So in all our illustrations in physics or current electricity, we will always look at conventional flow. So this will be the basis of our conventional flow. Will be the basis of our explanations, conventional flow, not electron flow. So you'll notice this is the symbol for a variable resistor. It can also be drawn like this with an arrow. Once you see the arrow like that, it simply means it's a variable resistor. That arrow simply represents a knob which you are able to vary or change the voltage, or rather the current flow. So that's a variable resistor. This is another symbol for it. And then this one is called a fixed resistor. You can also illustrate it like this. It doesn't have an arrow. So the difference in the symbol for a rheostat or a variable resistor and a fixed resistor is that a fixed resistor doesn't have an arrow, yet the rheostat or a variable resistor will always have an arrow. And of course, I cannot emphasize this enough, always you can only connect a voltmeter across a resistor, either a fixed or a variable one, and then across a cell, normally a battery in this case, because there are two. It is one, it's a cell. Then we have this one. This is an ammeter. Sometimes an ammeter is illustrated with a bulb like this, the symbol Ebaganje. Sometimes even Ganje. So this simply represents a bulb, and it's the same as an ammeter, because an ammeter will be connected across a bulb. So these are the main basic. We do have more, the Faraday relay, conductors, and even when it comes to transformers. But these are the main ones that we will be using to explain, describe and demonstrate any electrical phenomena. Alright, now having looked at this, I want us now to go to the explanation of what we call Ohm's law, because that will be the basis. This law is very important. The reason it is important is because it will form the backbone of our study in electrical current. Because the equation that we shall learn now, you'll need to recall it. So you need to find a way and practice and make sure that it is embedded in your heart. Because it's the basic formula or equation that will also include the many others that we shall learn. So Ohm's law basically states that voltage is directly proportional. Voltage is directly proportional to the current flowing. Voltage is directly proportional to the current flowing in a conductor, in an ohmic conductor. Now I'm sure this can also raise the question, what is an ohmic conductor? So basically this law tells us that there is a direct proportionality between current and voltage, and also there's a direct proportionality between voltage and current. So hence, remember the symbol of proportionality, which we call alpha. So notice I'll make some sketch of how Ohms discovered this. By the way, this is a person again. Ohms. So you'll notice most of these scientific phenomena, that is why even today, when we were learning about the laws of Newton's moon, his name was Isaac. So this particular guy is George Simon Ohms. He was a German physicist and mathematician who came up with this. So he did some experiments. So maybe before I show the experiments that he did, this would become V is equals to IR. So basically R will be the constant that we will measure or that we will find for an ohmic conductor. Now one specific example of an ohmic conductor is constantan. So constantan, this is just an alloy which is made out of 55% copper and 45% nickel. So this is our. So the experiments that he did, there are two, and they both gave the same results. The first one, what he did, he varied current, and the second one was varying voltage. So what he did was, he made a basic circuit, or he created a basic circuit. Now let's say this one has some cells in there. And because you will be varying current, how do you vary current? We use a variable resistor. So he connected a variable resistor, and then he put the material, which is the constantan in this case, the wire. And then of course, you can still have your fixed resistor still there. And then all he had to do was to control the current using this so that you can measure also and find out the output, which would be the voltage. Because remember, now we will have our voltage flowing in the circuit, so the current will be affected by the varying of the current using the resistor, and this will also be read by the fixed resistor, which will be the current that is flowing in the constantan of the wire or within the circuit. And then what he did, he tabulated his results. So varying current means you are having the independent variable as your current. So let's have 0 and let's say 0.1, 0.15, 0.2, 0.3. So and then he measured. So how did he measure? So remember, you have a fixed number of cells. The only change that you are making is the amount of current that is flowing. So when the current is 0, when there is no flow, obviously you have 0. And then you will control the variable resistor so that it has a current flowing of 0.1, and then you would register the corresponding voltage as read by the voltmeter. And again, you do the same for 0.15 current, a 0.2, and a 0.3. Then you would record his results. Then when it comes to varying the voltage, he also had a simple circuit. Now in this case, basic attention or the main attention will be focused on the cell, or rather the EMF. So still we have that particular circuit. So in this case, what we'll be focusing mainly on is the change. In fact, we don't even need the constant wire. So in this particular cell now, you are only changing the number of cells. So our focusing point now, we're changing the current through the variable resistor. Now we are changing the voltage by increasing the number of cells. So what you would do, you would record, start by, of course, the initial one should always be 0, then 1.0, 2.0, 3.0, 4.0. So in other words, let's say a single cell would give you a voltage of 1, and then you add them in increasing or in ascending order. Fagama cells learn to record the current. So the current obviously will be, I forgot to put an ammeter. So obviously we record the current that is flowing within the circuit. So through the ammeter. So using the ammeter, you record what would be the current. So you record what would be the current for all these. And hence, he would find the results. And then the results that he recorded, he then drew up a graph to illustrate the relationship between current and voltage, or voltage and current. So for this particular graph where he was varying the current, he noted that it was like this. So remember, when you're varying current, that would mean your independent variable would be the current, and your dependent variable would be the voltage, because it is depending on how much current I have. So he noted that there was a completely linear graph or a line which is passing through the origin. And when you find the gradient of this line, you will notice that it will give you the resistance, because this is V against I. V against I, why? Because Ohm's law is V is equals to IR. So when you divide both sides by I, notice that R is equals to V over I. So V is the y-axis and I is the x-axis. So this is called the theoretical experiment for Ohm's law. So this is a theoretical experiment. Theoretical experiment for Ohm's law. In which case, when you find the gradient of the graph, it will give you the resistance. Now, with this one, the graph was like this. Now, voltage will be now the independent variable, and I is the dependent variable. So still, the graph passes through the origin. So it is more or less the same. However, it is more or less the same. This is the experimental graph. So in this experimental graph, that was the theoretical graph. So in the experimental graph, if you are going to find the gradient, you will notice that the gradient will be a reciprocated resistance, meaning it over I over V, which is actually 1 over R. Now, I don't like this one. However, I cannot determine how the question will be asked in an exam, but I can give you a clue on how to solve a case where you are given like this or like that. So when it is like this, it is easy. You can always find the gradient and it will give you the resistance as it is. But the problem with this one, would say, this one is I against V, which means it is reciprocated, or I over V. So the answer, the gradient that you will get now, you will have to reciprocate it. Meaning, so that you get the correct answer as a resistance. Now, another solution to this, so that you get the same value, let me give an example. This is how I always encourage learners to do. So to solve the struggle of reciprocating, because if you are given like this, one can't also reciprocate. So to solve this is what you do. Let's say the voltage now it is 2 and the current now it is 0.5. So I'll use the same figures now and just only, so our voltage is 2 and our current is 0.5. So what you should do then, so since we know Ohm's law, remember I said this is the backbone of current electricity, you need to recall this. Make sure you remember it. So when you're given a question like this and you're asked to determine the resistance given the graph, you just need to pick one point. So in both cases, pick one point. In other words, you pick a value of the voltage with its corresponding current. So for instance, in this case, the point is 0.5, 2, and in other, the point is 2, 0.5. So either way, what you should do, having recalled the formula for V is equals to IR, which is Ohm's law, make the resistance the subject of the formula, so which will be V over I. So divide by I. And then, so 70 in both cases, use that point, and I tell you, you get the same answer without having to find the gradient and obviously reciprocate. So what you do, what's my value of V? 2. What's my value of I? 0.5. So please find the value of this. I think it should be what? 4. But just for this, check using a calculator. Because this is 1 over 2. 2 divided by 1 over 2 is the same as 2 times 2 over 1. So that should be 4. Now, the units for ohms, rather the units for resistance is ohms. This is an uppercase Greek letter called omega. So this is a unit for resistance. And then of course, remember we're trying to avoid a case where we should remember to reciprocates, especially in an experimental graph. So now the same thing. Look for that specific point. It doesn't matter if it's I against V. The value of V is still 2, and the value of I is still 0.5. It doesn't matter where it is. And of course, still you get the same answer as for ohms. This is how you can solve the problem of trying to recall the fact that you need to reciprocate the I against V. So this is how we solve Ohm's law, or how we prove Ohm's law in terms of calculating the resistance. Now, of course, a simple example, I think I have already highlighted one example of an ohmic conductor is constantan, which is the best material. It has a constant electrical conductivity or a constant resistance. So it's an efficient material. It's an alloy that is normally used in many electrical conductors. Now, examples of non-ohmic conductors, which means those do not obey this law. There is one which is called tungsten. Tungsten, those, they use a lot of current because they have a lot of resistance. So those are non-ohmic. Another one is called the thermistor. Now that one is made out of the silicon. It's also called the silistor. That one is a alarms. So that is also not a ohmic conductor. It does not obey this law. So mainly this is where we park it when it comes to current electricity. I think our next lesson should be continuation, where we shall look at series circuit versus parallel circuit. Otherwise, today we have just covered the quantities of electrical, of current electricity, looking at current, looking at voltage and resistance, and then we concluded with what Ohm's law is, so that we can have an understanding on how we can calculate resistance when we're given a graph, either a theoretical graph or an experimental graph. So next time, like I said, please remember this. We shall use this as an important application in the different types of circuits, parallel, series and parallel. And we shall have fun looking at that. Otherwise, cheers for today.